it's 98% humidity. Let's suppose that I filled my entire house with that air. In my entire house, there'd only be about 1 cup of water in the whole house. So pretty dry and not much water in the house. But in reality, it was 67 degrees in the house and it was 24% humidity. So in that conditions, there were actually about 4 cups of water in the house. So that's still pretty dry, but it's Maine in the winter, so you'd expect it to be dry. But quite a bit more than would be outside. And then finally, what's the maximum capacity if I fully saturated the air in my house at that 67 degrees at 100% humidity? It could hold up to 18 cups of water in the whole house. So I think the kind of 2 points I want to make on this slide is that first, this warmer air, 67 degrees, can hold way more water than that really cold air. So that's 1 point. And then the second point I want to make is that looking at the indoor and outdoor conditions, there are basically 3 more cups of water in my house than if I had just taken that outdoor air and warmed it up. So where did that extra water come from? So moisture in your home typically comes from sources like infiltration, whole house ventilation if you have it, cooking, bathing, building materials drying out if it's a new construction. And you can kind of think of humidity control as a balancing act. So it's moisture coming into the house and moisture going out of the house. So how is moisture removed? Primarily, that's the job of an air conditioner. It's cooling the air in your house, but it's also dehumidifying it at the same time. And then the other main way to get moisture out is through local ventilation. If it's in a kitchen exhaust, bathroom exhaust, you're removing moisture kind of directly from the source. Finally, if you have more moisture coming into the house than going out, you're going to see increasing humidity. So that's kind of why I see it as a balancing act here. So kind of what we're going to talk about today when we think about humidity control, one good way to think about it is this balancing act. You're going to look at ways to reduce moisture coming into the house, and you're going to try and optimize ways to get it out of the house. So think of those 2 sides of the equation. So you all chose to be on this webinar today, so I assume you know why. But why do we care about high humidity at all? First, it's uncomfortable. That's usually obvious. Besides being uncomfortable, there are some issues. You can lead to high humidity can lead to mold growth, growth of biological pollutants. So that's running into health concerns, particularly with people with asthma or allergies. And in some cases, you can also run into situations where you get rot and decay of building materials like framing and drywall. So high humidity can be a comfort issue, but that it can also be an issue of health and safety. And a general recommendation from a couple different sources is if you keep indoor air relative humidity below 60%, you're probably not going to run into any of these serious issues. So I'll mention that a few times during this. 60% is a good target to try and keep things under. So I'm talking about humidity control primarily because efficient homes tend to do a good job decreasing sensible load, but not so much latent load. So sensible load being temperature driven, and latent load being moisture driven. So this is true for a home with just a low HERS index. It's true for an Energy Star home, modern code built homes, 2012, 2015 IACC homes. Those can run into these issues as well. That's primarily because most efficiency improvements are decreasing sensible load and not latent load as much. So kind of think about typical upgrades. You're looking at better windows, more insulation, efficient appliances, lighting. None of those really impact moisture in the house. They don't really change latent loads much at all. And you might say more efficient homes, they're tighter. They have lower infiltration. That's going to drive down latent loads. I'd say yeah, but then remember that oftentimes code now and Energy Star and other programs require whole house ventilation for indoor air quality. So we're kind of undoing some of that decrease in infiltrations. We're adding back some of that latent load in these more efficient homes for indoor air quality. So what happens is in these efficient homes, we have relatively high latent loads, and then that puts us at a risk of potentially oversizing, sizing equipment just improperly, and setting up equipment to be short cycling and not dehumidifying properly. So we kind of need to figure out ways to have efficient homes, but also at the same time manage humidity so that they're healthy and comfortable to live in. So this is my last background slide. Just wanted to quickly go over how an air conditioner dehumidifies and what's going on in an oversized system, why that's a problem. So I have my little diagram here of an air conditioner, and we have warm air coming in, going across those cold coils, and as it cools down, you get condensation on the coils. That's water being removed from the air, and after like 10 or 15 minutes, something like that, you get enough water where it starts to drip off the coils and drain away. So that's how your air conditioner is dehumidifying. It only works if you have enough time for that water to be able to collect and actually drain away and drip off. If it doesn't run for long enough, it's not really dehumidifying. So with an oversized system, yeah, same thing's happening. You got air going over the coils, cooling down, but it reaches its set point faster and it shuts off before there's enough time for the water to drain away. So any little bit of water that condensed on the coils ends up just evaporating back into the living space. So this is called short cycling. You're basically cooling the air, but you're not dehumidifying it. And it's really because it's not running long enough. So that's why it's important to size equipment properly. It's kind of critical for humidity control. And so let's go on to the next slides and suggestions and best practices for how to manage this. So these next slides are based on some research, like a little bit of a literature review I did last year. So I'm with ICF. I support mostly the Energy Star program, but we also implement new homes programs for utilities. And in one of those programs, we had builders in the Mid-Atlantic that were having trouble with high humidity. To fix this, they'd been going back into their homes and installing supplemental dehumidification, like after the homeowners had moved in. So this was a pain, it was expensive. They definitely didn't want this to be a long-term solution. Primarily, they were asking us about guidance on whole house ventilation, what strategies to use. But then they also wanted to know low or no cost things they could do to help with humidity control. So we did some digging, gave them some recommendations, and then we ultimately kind of documented that in a white paper. And the gist of the paper is make sure you do these things right before you go to adding supplemental dehumidification. And so I'm not saying that everything I mentioned guarantees you won't ever see high humidity indoors, but it's going to lower your risk of it. And if you do end up installing supplemental dehumidification later, that means it could be a smaller system, or it could run less often and use less energy and ultimately cost the homeowner less to run in the long term. So moving on to these solutions that I kind of recommend. So the first set is focused on the HVAC system. I think this might be the most important thing to do, sizing your HVAC system properly. I do have this little logo here when one of the things I recommend is part of the Energy Star program. So this is part of the Energy Star program. But then there are also things that I talk about that go above and beyond Energy Star requirements. So for sizing, use industry standard practices like ACA Manual J. Make sure the design of the home accurately reflects the actual home. You know, it's the right size, has the right amount of windows. Make sure, you know, they're comparable and they're close to each other. So second is then taking that load, Properly sizing the equipment, ACA Manual S, good industry standard around this. Part of that standard is making sure it has enough sensible and latent capacity to be able to control temperature and humidity. And then finally, limit oversizing as much as possible. You're working within, what equipment is available for you, so you'll never be able to hit your load exactly, but try and limit oversizing as much as possible. I talked about why it's bad for humidity control. Frank has some examples about this, how it caused some real headaches. So hopefully we'll put forward a good argument that you all can take out there and try not to oversize equipment. And I think I just have this one slide on this, but I know we had a plug for Wes Davis's presentation coming up, so I'm sure he'll be able to speak much more to the value of these standards than I will. So next up for HVAC equipment is commissioning. Again, this is part of the Energy Star program. If you have an accurate load and select equipment that's going to be a good fit for your home, you want to make sure when it's installed, it actually performs like it's designed. There are kind of a few key things to verify. They're all part of the Energy Star program already, which is based on ACA's QI5 standard. And there's a lot going on in the industry, like ResNet, for example, with the HVAC grading standard. I think if Dean Gamble at EPA is going to be talking about that coming up soon, which I would highly encourage listening to that. So there are a lot of resources out there to try and help support proper commissioning of HVAC systems. I think the most important things to look at are limiting duct leakage, making sure your equipment has proper airflow through the blower fan, making sure the air conditioner has enough refrigerant, it's charged properly, not over or undercharged. There are other aspects of commissioning, but I don't want to walk through them all in detail. But my main point is just to make sure equipment is commissioned. There are a lot of resources out there to help you do this. So next up is paying attention to the equipment sensible heat ratio. So first up, sensible heat ratio basically represents how much of the total equipment capacity is sensible or latent. A lower sensible heat ratio means you have a higher latent capacity and more availability to dehumidify and handle latent load. So as an example, over on the right here, so say you're comparing a 14 and a 16 SEER, trying to choose between. In this example, the 14 SEER unit has a lower sensible heat ratio, and therefore it's got a larger latent capacity. If you're struggling with humidity control, then that 14 SEER unit might be a better option. My point's not to encourage less efficient equipment, but it's definitely to pay attention to this, the latent capacity of the equipment you're looking at. Maybe that 16 SEER unit has enough latent capacity, then I'd say great, use it, go for it. But if it doesn't and you end up using it just because it's more efficient, you might be setting yourself up for trouble. Last point on this slide I want to make is that kind of like everything with HVAC design and air conditioners, sensible heat ratio and latent capacity change with outdoor air and indoor air conditions. So when you're doing a manual J load calculation, that evaluates a home at its peak conditions, basically kind of looking at the hottest day of the year, making sure it can, keep the house comfortable at those peak conditions. But you might want to also look at off-peak conditions to see what the loads on the home look like on a warm but not the hottest day, and see if the equipment has enough capacity for that at those conditions. So basically 2 points here: pay attention to latent capacity, and then also consider evaluating that at off-peak conditions. So the next solution is something called supply fan overrun. This is a feature of air conditioners that it supplies a little bit of extra cooling and it actually increases a product's SEER rating. So overall, that sounds like a great thing. But one drawback is that it actually adds moisture back into the living space that otherwise would have been removed. So let me explain how this works. I'll have my similar little diagram here. And we have airflow going over the cold coils, water is condensing, draining off. Great. It meets its indoor set point. What happens is the condenser shuts off, but the fan keeps going. So the coils cool down and it squeezes out a little bit of a leftover cooling from the coil. So that's where you get your kind of efficiency boost. But when it does this, it actually blows that water that had condensed on the coil right back out into the living space. So that last little bit of dehumidification that you did is basically reversed. It's sent back out into the home. So if you're in a really dry climate, say you're in Arizona, it's not going to be a bad thing. But if you're somewhere else, maybe you're in Houston and you're having trouble with humidity, that might not be the greatest thing for the home. And supply fan overrun might be making the problem worse. So what do you do? HVAC contractors can disable supply fan overrun, and you can get a decent benefit. So one study I looked at, which the link to it as at the bottom, and I think these slides will be shared. But one study that FSEC did showed in Miami, a unit with 90 seconds of overrun, undoing that 90 seconds basically saved 1,300 hours above 60% humidity. That's 53 days worth, a couple months. So depending on where you are, this could have a really huge impact on humidity control. So that was kind of the most extreme example in the study they looked at, but I just wanted to illustrate the point that, potentially this could be a big impact. So that's one thing to consider is supply fan overrun. So next couple slides, I'm going to talk about ventilation. Before I was talking about HVAC equipment, the first one on here is local mechanical exhaust. Besides an air conditioner, this is the next way to remove moisture directly from a home. In this case, kind of directly from the source, the kitchen or the bathroom. So a couple of suggestions here. Make sure you measure the ventilation rate, that it's meeting its requirements per ASHRAE 62.2, and then verify that it's actually getting that air outdoors. So just suppose for a bathroom, you have a fan, it's pulling 55 CFM, it's getting all the way outdoors, that's great. But you could have the same fan, you could have an undersized duct, it could kind of take a roundabout path, and you find it's only pulling 25 CFM, that's not going to work. And then what if you followed that ductwork and you found it was venting into the attic instead of outside? That's definitely going to cause a problem down the road. So from the perspective from the bathroom, if you're standing in the shower looking up, it's going to look like the same bath fan, those two scenarios, unless someone actually verifies that it's pulling enough air, if they measure it and they verify that their air is actually getting outdoors. So that's an important thing. Just having a bath fan isn't enough. You got to make sure that it's working properly. So next up is whole house mechanical ventilation. So code requires this, Energy Star requires this, but it's basically up to builders to decide what type of ventilation is best for them. Typically, you're going to be looking at exhaust systems, supply systems, and balance systems like an ERV or an HRV. Exhaust would be pulling air out of the house. Supply would be forcing it into the house. Typically, that's done with an air handler itself. And then finally, there are balance systems, which you have at the same time fans that pull air out of the house and bring it in. You kind of have fans going both ways, pushing in and bringing out. And while they're doing this, the air can go through a heat exchanger to basically precondition the incoming air, and you get a little bit of an efficiency boost from that. So I have ERV listed here because unlike an HRV, an ERV does recover some latent heat, which can help with humidity control some. So which one of these is best for humidity control? I linked to a study at the bottom here that kind of looks to answer that question that NREL did. And of course, there's going to be a lot of variation based on the home you're looking at, where it's located. But the gist of what they found is that an exhaust system is basically going to be the worst from a humidity perspective. A supply system does a little bit better, and ERVs tend to do the best. So I do want to specify that an ERV, it's not actually dehumidifying the house. I think I've heard some people say that sometimes. I describe it more as an ERV adds a smaller latent load to your house than an exhaust or a supply system. So it's basically just adding a smaller load to your house. It's not actually dehumidifying, I'd say. But they do tend to be an expensive ventilation option, but you could see this humidity benefit from them. So my last slide on solutions is trying to educate homeowners. So I think occupant behavior can be a big driver of what happens in the house, and it's often hard to predict. I know Frank is going to talk about this a little bit further, but some kind of 3 little brief tips I'd say is try and have people use their local ventilation, or if you don't think they will, maybe you hardwire it to the light switch, the fan to the light switch, or you install ventilation with humidistat control so it stays on when it needs to. Another tip is if it's humid inside, I think it's often hard to kind of describe that, it's your air conditioner actually doing the dehumidification. So if you have your thermostat set point really high, it's not going to be able to dehumidify and remove that moisture. So you have to have it, low enough so it's actually working to be able to, lower the humidity in your house. And last thing is for your thermostat, set it to auto, not on. If it's on mode, that's going to waste energy. It's basically going to cause the same issue I described when I talked about supply fan overrun. So I'm sure for lots of you, this has, put some ideas in your head on things you've seen people do. I've talked to people after giving this presentation about, bad examples they've had, but kind of main point is occupant behavior can have a big contributing factor for humidity. So trying to educate people about that is another solution I'd have. So I've been mostly generalizing what to do for humidity, and I've pointed at some studies that you can look at that have numbers to back things up. But a little while ago, I decided to do modeling on my own to show the impact. I used BOPT, which is a software that DOE developed that has basically a moisture model in it, so you can look at kind of the humidity impact in the house. So the example I looked at was an Energy Star version 3.1 home in Maryland, because this request kind of originated from the Mid-Atlantic region. So, and it's a pretty efficient house, version 3.1. And so first thing I looked at was, well, where do these high humidity events happen? So what hours of the year was it over 60%? We basically only see it when there is cooling going on, so May to October in this range. And it's definitely not peaking during the hottest days of the year. You see like August, for example, or May, June, and September all have more hours over 60% relative humidity. That's indoors than August. So it's not necessarily lining up with the hottest day of the year. And you tend to see it more when it's, warm but not hot and humid out. So it's those shoulder seasons where we start to see it, these events more. So what I did, I decided to just look at a couple things. So I took that version 3.1 home in Maryland, and at first we started it at 964 hours above 60%. And I wanted to see how much of an impact some of the things I talked about today have on that. So first, I looked at bathroom exhaust. To do this, there wasn't a great way to model it, but what I did was I basically cut the number of showers in half and said, let's assume we're cutting the latent load in half. We're doing a really good job getting that moisture out. So that only cut 9 hours. Not a huge impact, but I think it's, you know, partially a result of the modeling of quirk there, and I think you'd probably see some localized humidity issues in the bathroom, more likely to get condensation on surfaces, things like that. So from a whole house perspective, not a huge impact, the local ventilation, but I think you could run into some localized problems with that. So second one I looked at that I didn't talk about, but I was curious for myself, was I swapped out, I had a gas water heater in the home, and I swapped it out and said, what happens if we put a heat pump water heater? Because heat pump water heater, as they heat the water up, they're also cooling and dehumidifying the space around them to do that. It's basically working, you know, kind of like an air conditioner does. It's dehumidifying at the same time. So the big assumption here is that I put it in the conditioned space. Could be a challenge in practice for some home designs, but I wanted to see what the impact was, and it cut 54 hours. So, you know, a little bit of a boost, but not huge. Third one I looked at was I took the air conditioner, basically gave it more latent capacity. I lowered the sensible heat ratio. That was a pretty decent impact, 192 hours. So we're starting to cut into that total. And then the last thing I looked at was I switched from using an exhaust system to an ERV in the home. That was a big change, 520 hours it cut off. So that ventilation strategy was a huge driver of those high humidity events. So put them all together, we got down to 320 hours. That's cutting it about a third of what we started. It's about 27 days worth. So that's, you know, a big change, and definitely most of it was from that the ventilation strategy that was used in that home. So I mentioned earlier a study by NREL that looked at different ventilation strategies, but I wanted to look at the home that I was looking at in Maryland for myself. So the 4 different strategies I looked at, exhaust supply, HRV, and an ERV. First, looking at just the total energy cost of the home. So this is electric, gas, everything. This is for the whole house. And it's a pretty efficient home to start. So between these options, there wasn't a big change in the total energy bill. Supply had the most, but you know, ERVs and HRVs, while they're efficient, they weren't really saving more than a few bucks a year over the exhaust system. So from an energy perspective, we really weren't getting a big benefit from this home. But if you look at the humidity impact based on these different types of systems, you'll see that the supply system saves a little bit. The HRV, you know, doesn't really change it that much, but the ERV saves a ton. So if you're just looking at choosing between these systems, you're not really seeing much of a change when you look at energy, but you see a big impact on humidity depending on what system you look at. And then, so one thing I did was that home, I swapped it out and I put it close to the 2012 IECC. This is my last slide on these numbers. And I said, let's pretend we're looking at options to improve the efficiency of the home, lower the ERI or the HERS index. So at baseline, we're starting at 69, and say we're weighing 2 different options, window upgrade or a 16-SEER air conditioner upgrade. Both of them get us 1 ERI or HERS point. So pretend we're deciding which one to choose. So we'd say, well, how much do they cost? Well, the window upgrade you're looking at is really pricey, about $2,500, but the incremental to get to a 16-SEER from whatever you're using, like 14-SEER to begin with, was a lot cheaper. So we'd say, well, definitely, if you're trying to get that one extra HERS point, definitely go with the 16-SEER air conditioner. So we're not happy with just that 1 point. So then we look at a couple options to get us down to an ERI or HERS of 62. So we have our tankless hot water heater, tankless gas hot water heater, or an ERV. They both get us to 62. The tankless water heater is a little over $300 cheaper. So we'd say that would be, from an economics perspective, that would be the better one to choose. That would get you there for the least amount of money. You can probably guess where I'm going next. But then if we look at these, first three measures, you don't really see much of a change at all in terms of their impact on the humidity in the home. But the ERV has a huge impact on humidity in the home. So after I put these together, I thought I should mention that I'm not an ERV salesman. I don't have any stock in them. It just happened to be a good way to illustrate humidity impacts. And some of the key takeaways from these slides I just wanted to illustrate. I threw a bunch of numbers at you in these last three slides. That was for an example home in Maryland, not applicable to anything anyone on the call right now is probably doing. And honestly, I don't think those numbers I talked about are that important, those exact numbers. They're going to be unique to every house and every location. There are a lot of people that can figure them out for themselves. I use BOPT. It's a free software from DOE. It's just as easy to use as any rating software that's available today, like REMrate, Ecotrope, Energy Gauge. Anyone familiar with those could pick this up and use it. The key point I want to make is that when we're looking at options to improve a home's efficiency, we often think about how much will it cost, how much will it save, and kind of balance those two. My suggestion is to also think about, well, what's the impact on humidity? Add that into the equation when you're considering these. So that is it for my slides, and I will now turn it over to Frank to give his portion of the presentation.
Very, very well done, Michael. I can see you're a modeling nerd like myself.
Can everyone, can you guys see my, we changed over to mine successfully here?
Looks good.
Okay. All right. Okay, everybody, here we go. So we, in setting up the presentation initially and selecting some case studies, Michael and I wanted to kind of cover a few things. We wanted to kind of do a single family and a multifamily. We wanted to cover a code project versus one that was participating in some above code programs. And then the third thing that we wanted to try to cover was kind of, in some cases, two different halves of this humidity issue. Sometimes it's an indoor air quality issue in terms of what the humidity level is in the home, and it's uncomfortable and, and can verge on unhealthy at sometimes. And then the other half of that is more when we have, serious condensation issues and duct sweating and the like. And sometimes you have both, but sometimes you only have one or the other, and they actually can sometimes be at odds with each other. So fortunately, fortunately or unfortunately, the last few summers out here in the Northeast have been quite bad. Summer of 2018 and 2019. So I had quite a few projects to pick from that we were having issues for. So we're going to look at this multifamily project first. So this was done 3-story, low-rise, kind of that garden-style building. It's very common in the Northeast, and I think really right across the country. This was in Delaware, so just a little bit south of where we're based out of in Jersey. But climate zone 4, about 4 miles in from the coast, so definitely in that kind of that coastal zone. Current energy code, or at least very recent with the 2012 IECC. Again, this was summer 2 years ago. And when I was brought in to kind of consult, said various units in the building. This is a multi-building project, so you had issues in apartments across different buildings that were having, very high indoor relative humidity above 70%, so uncomfortable. And then that was also activating mold growth. I'll apologize. I tend not to take pictures sometimes of folks' misery when we're looking at these kind of things. So I don't have photos of their mold, but basically had mold growth on, it was on door frames, on walls, and really any absorbent materials, clothes and furniture and any type of knickknacks that they had lying around. The clothes in the closets were particularly bad, just literally covered with mold. And this was, these were brand new, just constructed and just occupied buildings. So the field inspection and the analysis work that we did, just really kind of highlighted, just these fundamental design flaws and product selection and installation errors. One of the reasons why we chose this one, the first time Mike and I did this presentation was actually at the Energy Star conference. And some of the things that we're going to go through here, the Energy Star program is specifically designed to avoid. So that was the reason for my disclaimer here. This was not a HERS Rater or Energy Star project. It's a client that we do a lot of work with, but they happen to build this project without our assistance. So our involvement didn't start until they were having problems and called us in. So the next kind of bunch of slides are linked. I have some plan diagrams and some photos and things that we're going to look at. So there'll be some kind of documentation of these items as we go along. I didn't want to squeeze everything onto slides and make the text all small. So one of the issues we're going to look at is the engineer's sizing versus the contractor's equipment selection. I will say that we're not going to be letting the engineer completely off the hook here. We did a QC manual J on the apartments, and we found the engineer sizing was good. They have some other stuff to answer for that we'll look at, but their sizing was done in accordance with the ACA manual, so that was correct. We had some quote unquote unrelated value engineering that forced some MEP design changes, and that specifically impacting the return ductwork layout. We're going to talk about the engineer's basis of design equipment selection and its suitability to the architectural layout, which was particularly important for the system type in this apartment complex. The return air pathways, and then some of the things that the contractor tried to do once they started having issues before they called us in. So where we're going to start, and I'll show you a picture of the plan on the next page, from the contractor, we have a misread of equipment model numbers during equipment selection and purchasing. I assume that this is something very prevalent across the country. We get it all the time. EAM does a lot of MEP design in addition to being raters. So we're constantly getting HVAC submittals, and it's incredibly common, obviously, for contractors to submit a change request for the manufacturer of the equipment. That can be more or less problematic depending on how much time and effort they look into making sure they're making an equivalent selection, and also what the equipment type is. As you get into more complicated types of HVAC equipment, some of the heat pump stuff in particular, not everything is the same, and somebody really needs to be vetting when something's going to be changed. In this particular case, and I'll show you on the nameplates, we had the plan calling for 1-ton units of AC, which are available in the system type, and then they installed a 2-ton unit, and then they also doubled the heating as well. The plan called for the 24K version of the heater, and they ended up installing the 51. The second bullet point there has to do with those quote unquote unrelated changes that affected the return duct layout, and that was the alteration of the exterior balcony from a poured fiberglass deck to an open composite decking. So this is a zoom in of the final mechanical plan. So this is where I'm going to kind of knock on the engineer a little bit, because I can't see my audience. I won't use the words, but I'm sure you guys have the same saying that we do. It's a 4-letter word in, and then you get a 4-letter word out. We get a lot of plans through our office here. This was a 1-page mechanical plan for 24-unit multifamily apartment buildings. Normally you would get zoomed in separate unit layouts, in addition to full floor layouts. They kind of combined the two things on this. There were no equipment schedules, which is also, I think, a really terrible idea. The note that you kind of can see there in the top center, calling out the 9E Magic Pack unit with the model number, that constitutes the whole of the plan call out for the for the heating and cooling system selection. So, that's not good. That's poor, and you're setting yourself up for some difficulties there. You also have, again, this is the final version of the drawing. You had hand done red lines, and it was never actually really amended and reissued as kind of a high quality CAD drawing, which again I find to be lackluster in terms of provided engineering output product. So the issue that we had with the decking change that they made, and you can see that note about not being able to run outside, was that originally the ductwork for the return was supposed to run out of the balcony mechanical closet. These are, these single package vertical type systems. So you have a gas furnace packaged in together with a evaporator coil and a through wall condenser. Very common equipment across the country. So they were going to be running that return, and it was going to be able to go under the deck in a protected space. It was obviously be insulated and everything. And then come into the living area. So because they chose not to do that, and I'll have some pictures coming up so you can see it better, that causes issues with, that caused them problems with not being able to get the return into the central living space where you really wanted it. And they had instead large central returns that were only in the master bedroom, which is just highly problematic because the bedroom obviously operates in a different function from the rest of the house a lot of the time. In particular, I'm referring to the door being closed, and so not getting return air pathway for the entire unit. So the equipment selection issue, you can see the model number that was called out here. I know this sounds crazy, guys, but from investigating and talking with all involved, there was just carelessness here and a real inversion. The equipment number, this is the installed equipment. I blanked out the name of the manufacturer because honestly, it has nothing to do with the equipment. The equipment is fine. It's the selection of the sizing and the installation that's the issue. So I didn't want to have any, kind of knock-on effect there. And then this is the from the OEM manufacturer of the specified equipment that was on the plan. And in this scenario here, you have the gas output and input being referenced first, and then the cooling capacity. In the installed equipment, it's inverted. And like I said, it was just careless ordering, and they ended up, so they ended up with a 2-ton cooling unit where they were supposed to have 1 ton, and also double the heating capacity for the same reason. So, not off to a good start. The picture at the top is the transfer grill above the door to the master bedroom. So that's good that they have that, but it was by no means anywhere near adequate. You had probably a 12 by 18 return grill that was run through the wall from the HVAC equipment, and in a 2-ton unit, just using a general rule of thumb, I mean, you're moving about 800 CFM through that in cooling mode. This one small transfer grill was nowhere near enough to provide return air pathway to the rest of the apartment when that door was closed. So that was an issue. The bottom picture is a supply register that was cut in by the contractor. This was one of their fixes. I get what they were trying to do here a little bit by conditioning the mechanical closet, but I really don't like cutting in these kind of vents, particularly right off of an HVAC unit. It can introduce a lot of turbulence to the system. You also, that size grill right off the unit was losing an enormous amount of CFM, into that closet. So I get what they were thinking, but I don't like that as a solution. These are some more pictures of the mechanical closet. Some of the unit types did not even have a ducted return. They were just relying on the louvered door to the closet. Also problematic. You get a couple of coats of paint on that thing, and the net free flow area of those doors is not really where you need it to be. You can see in that central picture, they also decided to cut a return grill in the closet. Now this one I think is not defensible in any regard. You know, those mechanical closets in these style buildings are at best, you know, a sort of a waste conditioned, semi-conditioned space. So cutting that return in there was really, you know, this is an exterior type door with weather stripping. But actually when we arrived, they were actually letting the tenants have access to mechanical closets. They weren't locked out of them. So people were putting stuff in there. They were opening the door and not always closing it, or at least closing it properly. So you have this return in here now that is just sucking in outdoor air directly into the system, and you know, obviously pulling in all that humidity with it. This was a picture on the right of before they had added insulation. So some of the units, even before they cut the returns in, because they were letting people put items in these closets, they were already causing damage to the you know, to the air coil here, to the, you know, to that piece of ductwork. So, and again, you know, introducing moisture from the outside in. Other issues in the fundamental vein. So no kitchen exhaust to the outside. They just had a recirc hood. These do not do anything for moisture control. They have, you know, at best a grease trap sort of a filter. You know, moisture just goes right in and then, you know, gets blown right back out and dispersed into the apartment. So, and then their bathrooms were a similar problem. They were using a in-wall product because they wanted to save the expense of penetrating their fire-rated ceiling and the cost involved with fire dampers and things there. So that's why they went with this sort of very slim profile but very weak fan with very, very narrow ducting. You know, ASHRAE 62.2 is going to look for 50 CFM intermittent out of a bathroom fan minimum in order to be able to clear that air. In this case, we were getting tested out at an average of 16, but really as low as 10. And so I like to use maybe like a 20-minute delayed off in a lot of our projects, that unless they, aside from using an occupancy sensor, which also works well, but if you're just doing an on-off switch, we do like a 20-minute delayed off timer. So, you know, at 50 CFM of air, you're gonna, you know, the amount of air that you're gonna move during that 20 minutes, a fan that's only moving 10 CFM, you're talking about it having to run hours and hours to move that same amount of air, and that's just really not gonna happen. The other thing too is that a good operating bath fan that's running during a shower event clears the air a lot more effectively while the vapor is in the air. Once you have it starting to settle and condense all kinds of surfaces, you're already kind of losing the battle anyway. So that was one of the reasons why the clothing in the master bedroom was horrifically moldy. There was a lot of moisture during the shower events that was not able to get out properly. And due to the extreme negative pressure that was being created in the master bedroom, the closet actually existed in between the bedroom and the bathroom. And, you know, we had moisture just kind of getting sucked right through that wall and soaking those clothing in that dark closet. And, you know, the mold growth was activated. So implemented solutions on this project. The HVAC equipment was swapped out for the correct size equipment. We removed the contractor improvements. The one thing we did retain was the mechanical closet insulation. The closets were then locked so that tenants couldn't get into them and interfere with any of the equipment operation. We added more transfer grills. The other, you know, one of the things that was needed for adding them, the contractor realized that was an issue later and tried adding adding a transfer grill themselves. You really have to be careful, especially in some apartments, and look at your layout, because there's really, if you look at it, there's really only one way that the tenant or the homeowner is likely to lay out the furniture. And so while, you know, they had added a lower wall transfer grill, they really added it in a location where that was just exactly where kind of a large piece of furniture was always going to go. So it was blocked and it wasn't doing anything. So we had to add some more in, you know, in a location that would actually flow some air. Not as aesthetically pleasing, but, you know, it was more important to get the system to work properly. And then the bath fans were replaced with, you know, with units that had a higher static capacity, and we did that delayed off switch to rectify that. So the facility management was also keeping dehumidifiers on site for some spot use where it was needed. Kind of like what Michael talked about, we did some tenant education on the system operation, you know, placing furniture that doesn't block transfer grills and supply air grills and return air grills. You know, interior doors, you know, leaving them open as much as possible, you know, and only really closing them when that privacy is needed. Slight little PSA, you know, for us, that, you know, that sometimes when folks have problems is when they finally realize that they need to do things differently. So, you know, going forward, we've been, you know, redoing the MEP design for the future buildings at that site. So, and 2019, I, you know, was, you know, happy to be able to report was, you know, was much better, and did not have, you know, reported issues of mold anymore, or indoor comfort issues from the tenants. So this next one is a single family project. And this is not a picture of ductwork, fortunately. This is a picture of my gutter, because I chose to take a picture of it instead of going to clean it, I guess, during a thunderstorm at one point. So, so, you know, sometimes you can, you know, builders and designers and stuff, you can meet all your code requirements or above code requirements and still get ducts that do this, that condense and drip. And the reason for that is that, you know, we still need to be making smart decisions. The requirements of the code and even above code programs, like Energy Star and others at this point, are not designed to keep you out of trouble entirely. You know, we're still responsible to make smart choices. So these were some 2-story single family homes in New Jersey, again, climate zone 4, although quite a far bit inland at this, for this project. We had, this was affordable housing. So there was a 2-bedroom version of the house and a 3-bedroom, no options. So, you know, very, very straightforward homes, not overly large either. You know, I mean, you're talking about you know, it's like a 1,500 square foot home ish. These were Energy Star certified and LEED for Home certified. We were having issues also during that same summer of 2019. And the decision was made to just do a few small fixes during that summer, and to see if we had some building drying issues, which I'll talk about again later. But and then, you know, unfortunately resurfaced in 2019 and had to do some further things. I would say fairly typical construction for like high-end energy type homes at this point, although probably the one item would be the R6 sheathing. Is insulated sheathing is probably not too common yet, but you know, R21 2x6, your low E vinyl argon windows, an R49 blown attic, you know, air sealing package for Energy Star and everything. So, you know, a pretty solid envelope. Exhaust only, ash rate 62.2 ventilation. So from Michael's part of the presentation, you can probably already know that that's going to be a contributing factor in maybe some of the problems. Single zone HVAC, it has had a variable speed gas furnace, but for this humidity issue, it's really the variability of the AC system that's the issue. And this is your kind of common single stage AC. All the ductwork was located in conditioned space. And I'll show you a piece of the mechanical plan. The interstitial cavity between the first and second floors is where it was. And the ductwork was not insulated. It wasn't needed to be for either code or for Energy Star or LEED by their requirements. And we got brought in, well, we were already part of the project. And then once occupation started, the home started, you know, kind of exhibiting some serious condensation issues on the drywall and the other building materials to, you know, bad enough to cause damage. So I will, you know, just as a disclaimer, I will say that, so, you know, we were highly involved in this project. You know, we did the Energy Star and LEED certifications, and we were also the HVAC designer for the home. So in doing this presentation, we're trying to give you guys the best information and clarity. So if in going back through this, I felt like we had designed something that wasn't to the requirements of the program, or if we had, messed something up with manual J, D, or S, or anything like that, I'm a hold my hand up kind of person, guys. So I'd be talking about that right now. These were really done, by the books and, and the rules of the Energy Code and Energy Star and LEED, and we still ran into trouble. So that's really what we're trying to highlight here, is that, you can't always just rely on the programs you're working under to save you. Still gotta make smart choices. So obviously here we're in plan view. So real quick, on the left there, you can see the utility closet where the furnace is located, and then kind of along that X-axis, if you will, you can see the trunk of the supply coming across the home all the way to the other side. That was installed in a drop soffit. And then, kind of along the Y-axis, you can see all those branch runs, teeing off as they, as we move across the home. So when we went to do, our kind of, we had done some visits to see it, the issues, and then we kind of really went one day and took a real in-depth look and did some testing and then an experiment that I'm going to show you later. When we did this at ResNet, I ran a little over time, so I'm not going to get too into the weeds here of all these numbers. We'll just kind of touch on some, and then I'll just describe the conditions a little bit more. You guys can always go back through later and look through the actual numbers if you want to. But so we went on a very typical day. I know you guys down in your area. I've been down to Houston and those kind of areas. I know you guys have some very, very hot and humid type weather, probably even in a place like Houston, maybe even gets worse than what we experience here. So we went on a nice, hot, humid summer type day. It's 86 when we got there, warmed up to 91 quite quickly. When we arrived, we had asked them to have the thermostat set up a little bit higher because this is affordable housing. There's property management, so we were able to kind of work with them a little bit. So you had a thermostat set and reading at 73 degrees. The standalone dehumidifier that had been installed in the home was set at 50% relative humidity and was reading at 57. What I am calling the supply air floor cavity. So guys, this is that interstitial cavity in between the first and second floor where all the ductwork was located. That's when you see me call that supply air floor cavity, that's what I'm talking about. And we're putting temperature probes up in there. That at that point was already colder than the house at 70.5 degrees with a relative humidity of 62. So there was no condensation on the ductwork at this time, and what we did was set the thermostat down to 70 in order to start driving us toward worst case conditions. After half an hour, we took readings again. So temperatures at the evaporator coil starting to come down, which you would expect, down to 60 degrees there, and the relative humidity at the evaporator coil supply air coming up, which also makes sense. It's getting colder, relative humidity is driving up. And is now in excess of 80 there. So at this point, that supply air floor cavity had already dropped by about 4 degrees down to 66. And the relative humidity was already spiking up, had already gone up about 10 points to about 72% there. So you now had that uninsulated duct surface. And this, I should say, was all sheet metal duct, no flex, and is starting to sweat. And that was because the duct surface temperature in places, especially back toward the unit, was going below 56 degrees, which was the calculated dew point for that air in that cavity at those above temperature and relative humidity conditions. I didn't include a picture, unfortunately, but on an IR camera, you guys, if you were looking at the ceiling, you could have drawn an extremely accurate layout of the ductwork because you could see, you could just see purple lines crisscrossing the floor in the bays that it was in as it cooled down. At this point, we let it run for another hour and a half, and then came back. The room air temperature was down to 72. The thermostat was still set to 70, so the system had been running the whole time. Quick little note there. If you're wondering why after 2 hours we're still seeing the temperature not going down that much, the decision was made to operate the home in the as-found conditions, because one of the problems we were having at this site was also, as Michael mentioned, some homeowner education type issues. The upstairs of the home actually had basically all the windows wide open, and in some cases fans running and pulling in outdoor air while they were also then running the whole house air conditioning system. So that was we decided to leave the system there because we were really looking for worst case in terms of this duct sweating issue. And we knew that by leaving that open, that's the way some of the tenants are actually operating their homes. And that's the reason why these systems are running and running and running and never shutting off, despite the very, very high quality thermal envelope. We wanted to mimic that in the test. So those are the readings from the evaporator coil now. So 59 degrees supply air temp and 80% of the relative humidity. And the system was working well at this point. The return air temperature was 72 at 60%. And the duct surface temperature in places was now down to 53 degrees, which was well below the dew point for the floor air in that cavity. So at this point, the ducts were now sweating heavily enough that we were seeing the kind of dripping that we knew was occurring, and that would be dripping down to drywall and other materials that were causing these issues with the building durability. So at this point, we did our kind of cavity ventilation test, which I'll show you in the coming slides. But just to recap our initial conclusion, the system was working well for conditioning the home's air. We did experiments in other homes where we did close all the windows and have the home actually set up properly, and it was meeting set point, and everything just fine. The indoor relative humidity was great. But the air in that floor cavity was not participating in that process in a positive way. It was 10 degrees colder, at least, than the air in the home, and it was just not able to hold on to the moisture. So the ducts were really both the problem and then where the problem was manifesting itself, so that they were subcooling the cavity space, by sort of conductive cooling, and then we're also becoming the condensating surface at the same time. So these were solid, these were not open web trusses, which was part of the problem. So the joist bays where the ducts were very confined. On the flip side of that, though, we were finding that temperature probes put up into joist bays without ducts were really at the same temperature as the rest of the living space. So it was clear to us, what that issue, was there. So the dew point in the cavity we calculated from all of our readings was about 59 degrees. So anything colder than that was going to be a condensing surface. And like I said, we were recording duct surface temperatures of 53 down to 53 degrees all over the place. So it's just really physics at that point. So the conclusion was we got to take some steps to do one of two things. We either need to make the ducts warmer, or we need to warm and dry the air around the ducts. So we decided to try this interstitial cavity ventilation test. The other option would have been to insulate the ductwork, but these were 24 homes that were completed and being lived in. That option was going to, in order to do that effectively, would have involved tearing down the entire first floor ceiling, and with sheetrock, dry times of spackle and paint, all that kind of stuff. Best case scenario, you would have had to have been moving each family out of the home for maybe a week at the absolute best case scenario, and probably slightly longer. So for those of you who don't know what a duct blaster fan is, that's the fan that raters use when we're pressure testing ductwork. So we use that because we have high control over the CFMs. So what we did was we installed a passive air vent in the laundry closet ceiling, which the laundry closet was right next to the mechanical closet. So the trunk of the supply trunk came right over top of that closet as it came off the furnace. So we installed that there, and then we hooked the duct blaster up to that passive vent, and we set it up to deliver 200 CFM to the cavity. We also cut another passive vent at the other end of that soffit, so that there was an exit point, and when we really wanted to encourage that airflow down the trunk line as opposed to kind of off in all random directions down the branch base. So we did that via flow hood. We found that 100 CFM was actually successfully transiting that soffit to the other end. And then the other 50% was being, lost to leakage cavity points in that, in that space. Now, that might sound bad. That was actually, at that test pressure though, was actually a pretty good check of the tightness of that band joist area in that cavity. So that was actually pretty good. So the air was transiting the cavity well. And basically we just we let that run for an hour and a half. The room air temperature was still, the room thermostat was still set at 72 degrees. I'm sorry, the thermostat was still set to 70. And we still had the room air temp at 72. So it still had been running the entire time. But that worst case duct surface temp went up from 53 up to 57 at worst, but was in most places was up way higher in the 60-degree range. And then the relative humidity in that cavity was now about 64%. So the AC system during that period, reached a steady state. The supply air temperature was 57 degrees and 80% relative humidity, and then a real good return air temperature and relative humidity of 71.5 and 56.5. So what we found at that point was that all of the condensation was gone. And again, it was just simple physics. So we had driven, by ventilating that cavity with the warmer air from the house, we had driven the dew point down to 52 degrees. So it was impossible for condensation to occur at that point because the coldest air in the system, even back at the evaporator coil, was 57 degrees. And the situation would have continued to improve with further running. So the other thing to note here was that we had really allowed the system to get out of control for worst casing it in terms of the duct sweating. In actual practice, the ventilation system would run in conjunction with the AC system, and so we really never allowed to even get to that point where it was beating and dripping sweat, condensation all over the place. So the final implemented measures at this project were the thermostats were locked out at 70 degrees as the minimum. Again, this was managed affordable housing, so they were able to do that. The residents, what Michael was talking about here, they were instructed to use the fan fan auto setting only. The standalone dehumidifiers, where they were made available, were going to be set to 45% relative humidity. I'll note on those that, those adding these wall-mounted or kind of R2D2 sort of style standalone dehumidifiers, I mean, it's something in a home that's having problems, but they, and maybe in a small apartment, they can have more value, but the problem with them is that they inject air and exhaust air in the same space. They're not creating any kind of a flow gradient. So in this case, they had installed, when they started having problems in the summer of 2018, they installed these wall-mounted dehumidifiers in that laundry closet because there was a convenient drain that could be used for the condensate. And they did a good job in that localized area, but because they're just pulling air and exhausting into the same space, they're not creating any kind of a flow gradient across the whole house. So they can be relatively ineffective, especially in larger spaces. The cooling fan speed we turned up, and this was to raise the supply air temperature. And then we also did the no supply fan overrun that Michael was talking about. So my note there about having to balance the living space humidity is kind of going back to what I was saying. Sometimes you can have these two different types of humidity problems in a home, this condensation issue versus the moist, the relative humidity and the comfort. When you're having a comfort issue, you would not turn the cooling fan speed down. Up, you would turn it down because you would actually want less CFM, less CFMs per ton of cooling. In this case, we actually wanted to deliver slightly warmer supply air because we wanted the ducts to stop getting so cold. Now we had to balance that though, because you could take that too far and then start having humidity issues with your with your actual indoor air quality. So that's a balance that has to be struck. There had been some mold growth around the drywall ceiling in the supply plenum above the evaporator coil because it was run tight and into contact with that. And so that was cut back, and insulation was extended, kind of slightly up into that cavity, kind of fully wrapping the supply plenum coming off the evaporator coil, and then it was sealed with foam. Again, just to create kind of that moisture break, so that the drywall was not wicking, moisture away from, condensation away from the supply plenum anymore. You had the passive air grills that we had installed at both ends of the soffit, and the mechanical ventilation system, and that was installed utilizing an HVAC relay control system. Guys, I don't want this to come off as any type of a normal scenario that should be looked at as like an actual option. It was sort of desperation in this particular case. In certain types of construction, you couldn't even do something like this potentially because of, of maybe of fire code issues. And, if this was a multifamily residence or something like that, you just couldn't do this kind of thing. Even in a single family residence, we, had to kind of talk with the local building department and get their kind of buy-in as well. So this was, I just really wanted to use this, this case study to illustrate how crucial it is to implement the measures that Michael was talking about, and a few kind of other ones I'm going to talk about here now, so that you don't get into a home with this kind of situation and have to do some kind of a crazy fix like this. And then, homeowner education, obviously, what that Michael touched on, and I was mentioning, so running your AC with windows wide open, and leaving exhaust fans on constantly, cleaning of the dehumidifier filters and the HVAC filters, just basic, we're really finding that can make, a whole lot of difference. So these are just some other, if some of the low cost and low impact measures don't work, these are some of the things that we're doing with our clients as a rater and as an MEP designer in order to help them improve their projects. Number one, just insulate all your ductwork regardless of location. This whole concept of conditioned space, for interstitial cavities and things, because they're in between conditioned space. It's not, it's not the same as it being in a vented attic. It's certainly not the same as it being outside, but it's not conditioned space either. It doesn't behave that way. Correctly sized systems run a lot, and that's good. They're supposed to. They're machines, and when they're designed correctly, that's fine. But they, they do run a lot, and so your duct surface temperatures in certain locations are going to run down low. The ducts are also now, in most places with good energy codes, are highly sealed, and they are not waste conditioning that interstitial space anymore. So just insulate the ductwork everywhere. You'll be glad you did. I know there's a little bit of a cost premium, but it's well worth it. Variable capacity AC equipment. Obviously, this is a more expensive option. But where you need to, you can really better match your sensible and latent loads a lot better. Michael, talked a lot about that. I'm not going to talk any more about that, but the matching that load pie of these high performance homes just can get done a lot better with some of these other types of equipment. And it can be the type of condenser I'm picturing here. That's more of a traditional one that you would pair with like a gas furnace. Or it can be, more of that inverter mini split type condenser as well. And also, a lot of those companies are doing pairing with furnaces and things now. It doesn't even have to be a full heat pump system in order to use that type of inverter driven outdoor condenser where you can get a lot of variability in the load. I will note, we are talking about variable compressor, variable speed condensers here. The variable speed furnace is not really helping you in this particular regard that much. And actually, we don't have time to go into it, but in some cases, actually, it can kind of hurt you a little bit. Be aware that really fully variable equipment, or at least many multi-stage equipment, is really what's needed if you want to use this as a solution. Most of your two-stage equipment, the minimum sizing goes up to 2 tons. So where you could get 1.5 ton equipment in the smallest size, in your kind of basic single-stage equipment, you're not going to be able to get that. And so that 2-stage equipment, when it ramps down, it's just going to go back to that 1.5 ton. And the problem that many of us run into is that as we're doing apartments and smaller homes and things, or smaller, even if it's a multi-zoned home and each individual zone needs that nice small piece of equipment, you just can't get it. You know, that 1.5 ton unit is already way too oversized. So consider that. Michael talked about ventilation options. I just wanted to kind of note that, you know, really try to keep the major specs of your project in line with each other. We see projects that spend a ton of money on certain areas, and then they have to shortchange others. And with this condensation issue in particular, this is really the worst thing that will, you know, the common denominator we'll see is it really, really well insulated and air sealed thermal envelope for, you know, meeting a energy code or above code program, and then pairing that with your basic single stage AC equipment and exhaust only ventilation. Just highly problematic. Spray foaming band joists. This area is notoriously leaky, and it's allowing moist air into the cavities where these cold ducts are located. So exactly where we don't want it to go. We've had builders who were building basically the exact same buildings, in some cases designed by like the same architects and engineers guys, same equipment, and they experienced fewer or no duct sweating issues, even with uninsulated ducts, because the one major spec difference I could point to was that they had closed cell spray foam to their band joists. That was really the only major difference. So that can be an effective solution in helping to cut down this as well. So HVAC systems and equipment selection, install zoned or multiple systems. You know, really try to highlight function over aesthetics. You know, you get a lot of aesthetic complaints about certain types of equipment, you know, mini split ductwork, you know, mini splits in particular. But at a certain point, as designers and as, you know, as building professionals, you know, you have to be honest with folks about what's possible. You know, we see a lot of designs in our area moving toward, you know, and they've been this way for a while, just extremely unfriendly to proper HVAC install. You know, nobody wants to see headers anywhere. They want flush headers. They want, you know, glass everywhere. There's nowhere to run ductwork effectively in a lot of cases. So, you know, you just have to be clear with people that, you know, sometimes you can't have your cake and eat it too. And the home layout that you're going for is not going to work with the HVAC system that you're, you know, proposing to use. So, so try to leverage those ductless technologies when you can. Obviously, you can't have duct sweat if they don't exist. Dehumidification systems as standalone. I totally agree with Michael that you should not just go to that as a first option. You know, a lot, you know, if you should be able to take care of a lot of these issues with proper design and equipment selection and installation. But that being said, we are finding that, you know, dedicated dehumidification systems that in many areas, ours included here in the Northeast, you know, that's always been viewed as a luxury item, and it may not be anymore, especially for your particular project and for what your, you know, what the end user is going to be expecting. Jason and I were talking about this before the call. Cooling expectations from people have gotten really, 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 you know, picky, and in recent years, you know, to the point of, you know, expecting these just crazy 30, 35 degree temperature differences from what the outdoor temperature is. And then also, you know, then not wanting to see any condensation or anything like that. So you just may not be able to, you know, deliver quality dehumidified air under all circumstances without a standalone dehumidification system. For most air conditioning systems, dehumidification is an uncontrolled byproduct. You know, we're not, in most cases, people are not using the more advanced systems and thermostats that are closing on humidity. You know, that thermostat is only closing on temperature. And so depending on what the indoor outdoor conditions are, you guys have coastal area down by you, just like we do. So it's not always that hot, humid day that's a problem. Sometimes we have high outdoor moisture loads during cooler outdoor temperatures because of that proximity to the water. So, you know, it's really, it can, you know, you just may need that dehumidification system at some point. Don't discount the interior moisture sources in these, you know, late code, late energy code and above code programs. These are tight homes. Bath moisture, cooking moisture, you know, you can't discount these things. So on the left there is a picture. This is from IBS. It's going to, you know, it's going to be starting in flagship equipment, but we're starting to see like Bluetooth connected ranges, so that your range hood automatically goes on when you use the cooktop. That'll start in their flagship products, but it'll filter down. On the right there is also a photo from IBS in Las Vegas back when we were allowed to travel. Those are showing some options from Broan, just showing the wealth of options that's available for very specific combinations of different controls for your ventilation systems, you know, occupancy sensors and humidity sensors, timer delays. So you really can find these solutions that are tailored to the needs of your project. I talked about this, restricting cooling operation range where you can. I understand this is not always an option. It's very difficult on high-end construction. Somebody buys $1 million home from you and you're going to tell them where they can set their thermostat. I understand that's problematic, but that's where the homeowner education comes in. But on some more low-cost type buildings where you're not going to be able to afford standalone dehumidification or variable capacity AC equipment and these different things, it just really may not be possible to allow the tenant to homeowner to operate the system however they want. When as system designers, you know, engineers are constrained to using, you know, correct indoor and outdoor design conditions and temperatures and everything. So you can't really kind of have the designer constrained really rigidly on the one end, and then the occupant is kind of in a free-for-all as far as operation goes, and not expect to have some problems sometimes. The other thing that we spent a lot of time looking at was best practices during construction. We had a lot of projects that were having moisture issues in some buildings and not in others, in multi-building projects. So that is just, you know, we kind of brought that down to a case of, you know, climatic conditions during certain key milestones of the project. Some strings at townhome projects where we had issues just unfortunately got dumped on and the framing got soaked right before a key milestone, like building wrap and roofing and things going on. And so they were starting out with much higher moisture contents in the framing. And we're finding that it can take 18 to 24 months for framing to really dry out in these above code and you know, tightly sealed projects, especially if you're in a coastal environment and you have a lot of high humidity outside. You know, you're not getting that drying gradient. It takes a long time. Location within the building is an issue. You're going to have more problems with this on the slab level than you are on the top floor. The top floor unit has more load on it, but then also the slab is an issue. Construction moves at a very rapid pace these days. Slabs generally are not allowed to fully cure. You know, people pour the slab and they go vertical. And, you know, you guys know some of these builders move fast and you're enclosing these buildings quickly. The slab is still putting off a lot of moisture. So that has to be monitored. We found subcontractor behavior needs to be monitored. If you're a builder, you know, if you can't require things of your tenants or homeowners, that's understandable. But I think certainly you can require your subcontractors. It's very common on projects to find windows and doors open on the later stages of projects, especially during, you know, spackle and painting, and then the AC cranked down to 65 degrees on the thermostat. So you're damaging buildings before people are even moving in. We're finding checking deliveries and not accepting lumber that is already too wet. You know, that can be difficult, I understand, especially if it's something that's a delivery item longer term, like trusses or something. But, you know, builders need, you know, people need to be clear with their suppliers that they're not going to accept deliveries of soaked lumber. You know, Michael and I were originally going to call this presentation "Death by 1,000 Cuts," but we got we thought that it was thought that was too negative of a title. You know, we're not saying that you need to do every single one of these things right. It's just that when you do too many of them wrong, you're going to have these problems. So every little thing you can do to lower the moisture content is really helpful. And so starting out with framing that's not as wet is really important. The time of year is huge. You know, when you know a building is going to have its initial occupation right in the peak of the summer, you have to be a lot more worried about that building than a building where people are going to move in January and they're going to be in heating mode for a while. If they're going to move in and they're going to crank that thermostat down because it's July, and the framing is still moist, you know, it's going to bring out some of these issues. And like I said, we've been trying to use these problem events and find silver linings, and you know, finally getting some traction with folks who maybe, you know, have resisted doing some of these things because they're not easy, and some of these things cost money. But you know, you can get people's attention if you know, they've had some of these issues. This is, I don't know how much for this audience, but this was more for raters and HVAC designers. Maybe it applies to code officials as well. This was just our recommendation that, you know, propose these best practices, try to get them in the specifications. And if, you know, if value engineering is going to come in and have to remove some of these things, just to make sure that you get that in writing, so that, you know, a year, 18 months later, if there's problems, you know, you have something to point to that was, you know, hey, we wanted all that ductwork to be insulated, and you guys VE'd it. We find it's critical these days to be aware of the technology options as much as you possibly can, because a lot of them can help, number one. But number two, it's, you know, you don't want to get that pushback later that, oh, well, you know, if you had told me that such and such a widget was available, oh yeah, I would have paid for it, I would have used it. It's easy to say those things later, but so it's important to really be up on those things as much as possible. You know, and for us in our role, to be a really good partner with our builders, because everyone's super busy, and you know, you need to do your part to make them aware sometimes that these options are available. That fourth bullet point, the third bullet point, I totally understand that is not possible on a lot of projects, public projects and things like that, where you have to accept equivalencies and things like that. But on a lot of private projects we work on, it's not. I kind of touched on that before. HVAC is getting more complicated. There's more divergence in the equipment, especially in certain system types, a lot of the VRF type systems and things. It's not as easy to just, you know, swap it out as it was maybe with you know, with a furnace or something, where you could say, okay, yeah, you don't want to use, you know, ABC furnace and you want to use XYZ, and you take a quick look and yeah, that's equivalent and we're good to go. You know, a lot of these projects are being really highly designed with specific pieces of equipment in mind, and late stage changes to different manufacturers really need to be vetted carefully. And then as far as manufacturers go, what we're finding these days is, you know, really try to find some knowledgeable OEM representatives to work with. On certain types of equipment, I will take a really, really good local rep who really knows their stuff and supports their equipment over another company whose equipment might be, you know, seen to be better or more efficient or whatever it is. But having that really, really knowledgeable local rep, be, you know, really critical in getting these systems to work properly. So we had these slides in here from this was kind of discussion and Q&A that we had in from that conference. Jason, I don't know if there were any questions. I know I kind of ran a little bit over time again. I apologize.
No worries. And you just, I answered a few as y'all have gone, just a few kind of easier ones. Yeah, I was 25 years ago, my first job for a city was as a property maintenance inspector. And I could have let you know there's at least 10% of affordable housing that runs the windows open with the air conditioner on. It's just going to happen. That's the way it's going to be.
Yeah.
I think that's really it. I love that supply fan overrun. I didn't even realize that. I grew up, my dad's a carpenter, so I grew up framing, and I'm a much better plumber and electrician and certainly carpenter than I am a mechanical contractor by a long shot. I didn't even know that was a real thing. Typically, is it a 90-second default on a fan overrun? Is that typical in the industry?
I think 90 seconds is pretty high. I use that more as an illustrative example of like the worst case scenario.
Okay.
I think 90 seconds is pretty high, but yeah, I think it ranges, but
I think Mike, I would agree with Michael. I think it ranges. I mean, to his other point about that the fan on setting basically does the same thing to you, and I would sort of put forward that it's very common to see people running their system with fan on.
Okay. And then someone wanted to ask you, just as asking you to maybe kind of briefly elaborate on the connection between air leakage and humidity issues, and how important air sealing is. Just quick thoughts on that.
You want to go first, Michael?
Yeah, I had a couple thoughts on that. I saw the question come in. The things that hopped into my mind were definitely in hotter locations, infiltration has a smaller impact on energy compared to a colder climate. So I think that's why often we'll see, in codes, higher infiltration in hotter climates. So that's one thing, but from a moisture perspective, it's still important. Basically, you're having uncontrolled air coming into the house. There's the old saying, build it tight, ventilate right. And so basically limiting infiltration and good air sealing lets you know how much outdoor air is coming into the house from ventilation for air quality. So kind of controlling it and having a known value. As far as like designing to it, the one thing I jumps to my head right away, there's probably a lot we could talk on this, is that your manual J, as much as possible, should reflect conditions of the house as it's built. So if you're working with the builder and they're always hitting 4 or 5 ACH 50, you should try and get your HVAC designer to use that value if they're pretty consistent around that. And then Energy Star, for example, has kind of guidance on manual J has defaults like tight and semi-tight and average. Energy Star has some guidance on what you should use on those for an Energy Star home at least. So if you're kind of building to infiltration rates similar to what Energy Star specs, you could look at those and give that guidance to your designer as well. And then if there's going to be a later webinar on the HVAC grading standard 310 from ACA, in that it actually has a requirement for that standard that the infiltration rates are in the design are within a tolerance of 2 ACH 50 to the actual home. So if you measure 4 ACH, in order to get grade 1 HVAC per that standard, the design has to be somewhere between 2 and 6, so plus or minus 2 ACH. So that standard does establish a tolerance for that. So I think high level, try and have your design reflect the house, and it's important to seal it up right. So kind of quick thoughts on that. I'm sure there's a ton to say about it, but first things that popped in my head.
No,
I would the only things I would add to that would be yeah, I mean obviously something like vapor diffusion through materials exists, but it's a much slower process. So most of that moisture moisture flow coming with air leakage is really that's your big driver of moisture coming in. I didn't really talk about it, but on that single family home project, we had also done some data logging. Those were, incredibly well, they were very well insulated and air sealed units. But again, they were using that exhaust only ventilation system. So we had done data logging where you could just, you could watch it just sit there and maintain temperature very well. Again, when the windows were not open, and you would see the thermostat maybe kick on for 10 minutes and satisfy, and then maybe not kick on again for over an hour because and this was on an August day, and it was just because of the quality of the insulation and the air sealing. Meanwhile, because of that exhaust only ventilation system, you were just watching the the relative humidity line just creep up and up and up. Because it was, it's a well air sealed home, but it's not, it's not a vacuum bubble. And that exhaust only ventilation system is just, letting that air come in wherever it can from the outside. And so it's, in a way, it's kind of almost mimicking a leaky envelope that wasn't well air sealed. So yeah, I mean, good air sealing, I think is incredibly important to try to controlling, moisture flows.
Yeah, that good old exhaust only ventilation, and the problems that it ultimately causes. To me, a couple of things, some sort of smart ventilation. I mean, in Houston, when it's 90% relative humidity and 92 degrees, I don't want any outdoor air coming in my house. So some sort of control, humidistat, something. And then also Houston, Beaumont, I know code is the crummiest house you can build legally. How there isn't some sort of supplemental whole house dehumidification requirement for the crummiest house you can build in really humid areas is kind of crazy to me. But that's just my opinion. Fantastic job, guys. I'd say the rumors were true. That was I love the kind of the simulations, how Michael started it out with the kind of the simulations and the science and the numbers, and then Frank with the case studies on the back end. I thought those two things went really well together. I can't thank you enough, guys. It was very well put together, very well done. Just a fantastic job. And Frank, you are far too kind. That mechanical design on that multifamily project, yeah. That's a plan I would reject with no other comments than submit a better mechanical plan.
Absolutely. Well, like I said, I can't complain too much because we're doing their MEP design now. So whoever drew that one up did me a favor, honestly.
There you go. Well, and then going forward, any MEP design for affordable housing, make sure design that on worst case scenario, because it's crazy what I've seen as a property maintenance inspector. Oh my goodness gracious. And it's everywhere though. Well, thanks so much for your time, gentlemen. I really, really appreciate it. Thanks for joining us, everyone. And we'll be back tomorrow with Wes Davis from ACA. Hope to have you on the call then. Michael, Frank,
Jason.
Can't thank you enough.
Thank you.
See you guys.
Bye.